Hello and welcome to this video. In this video, I will explain how to solve a numerical based around psychrometry chart to calculate total cooling load and room heat gain. So, example is like this. The air handling unit of an air conditioning plant supplies a total of 4500 cm of dry air, which comprises by weight 20% fresh air at 40 degrees Celsius dry bulb temperature, 27 degrees Celsius wet bulb temperature, and 80% recirculated air at 25 degrees Celsius dry bulb temperature and 50% relative humidity. The air leaves the cooling coil at 13 degrees Celsius saturated state. Calculate total cooling load and room heat gain. So here, as outside fresh air it is at 40 degrees Celsius dry bulb temperature, and recirculated air, which is room air, it is at 25 degrees Celsius. So this is numerical based around summer air conditioning system. So first we will draw layout for the system. So outside air it is the 0.1 and room condition it is 0.2. So this outside air and room air, that is recirculated air, it is mixed in the mixing chamber and then it is supplied to the cooling coil, and after that it is supplied to the room. So outside air it is 0.1, inside room condition is 0.2, after mixing it is 0.3, and after passing that air over the cooling coil, which is 0.4. So this is the typical layout for air conditioning plant. Now we will write the given data. So here supply air it is given 4500 cmm. Cmm means cubic meter per minute. So supply air, which is the combination of fresh air and recirculated air, so it is V3. So V3 is equal to 4500 meter cube per minute. Then 20% fresh air and 80% recirculated air is given. So we can add fresh air quantity, it is 20% of total air, and recirculated air it is 80% of total air by weight. Here fresh air means outside air condition is given. So we can write for fresh air dry bulb temperature, that is TD1, because outside condition we are indicating with 1. So dry bulb temperature, which is TD1, is equal to 40 degrees Celsius, and wet bulb temperature, that is TW1, it is 27 degrees Celsius. And recirculated air, it is the room air. Here properties of recirculated air, that is room air, it is given. So room condition it is 0.2. Here we can write 25 degrees Celsius dry bulb temperature means TD2, and 50% relative humidity means it is phi2. Then here it is given air leaves the cooling coil at 13 degrees Celsius. So after leaving this cooling coil at 0.4 temperature is given. Also it is saturated air, means relative humidity is 100%. So at 0.4 we can write TD4, and as it is saturated, dry bulb temperature is equal to wet bulb temperature, which is equal to dew point temperature. So that is 13 degrees Celsius. And as it is saturated state, relative humidity phi4 is equal to 100%. Then here it is asked to calculate total cooling load and room heat gain. So here properties of outside air, that is 0.1, it is given. Then properties at 0.2, that is inside room condition, or which is also recirculated air, it is given. Then at 0.4, that is after passing over the cooling coil, condition of the air is given. Also quantity of fresh air and recirculated air it is given, and we have to find total cooling load and room heat gain. So we will locate these 3 points on the psychrometry chart. So this is typical psychrometry chart. Now here we have to look at point 1, that is outside air condition. Dry bulb temperature 40 degrees Celsius and wet bulb temperature 27 degrees Celsius. So on x-axis it is dry bulb temperature. So here it is the 40 degrees Celsius. So from this point we can draw a vertical line, and wet bulb temperature 27 degrees Celsius. So here it is 25, then 26, 27. So from this 27 we can draw a line along constant wet bulb temperature line. These inclined lines are constant wet bulb temperature as well as constant enthalpy lines. So from this 27 degrees Celsius wet bulb temperature we can draw a line along constant variable temperature line, and intersection point it is the state 1, that is condition of outside air. Similarly, we have to locate condition of the air inside the room, that is point 2, or recirculated air. So here dry bulb temperature is 25 degrees Celsius and relative humidity 50%. So here it is dry bulb temperature 25 degrees Celsius. Draw vertical line from this, and here these curved lines are the relative humidity line. So this is 50% relative humidity line. So intersection point it is the state 2, that is state of the air inside the room or state of the recirculated air. Then at point 4, that is after passing that air over the cooling coil, condition is given. So here it is the dew point temperature 13 degrees Celsius and it is saturated air. So for saturated air, relative humidity is 100%. So this curve it is the saturated curve, and on this curve here it is 10, then 11, 12, and here it is 13. So this is 13 degrees Celsius and dry bulb temperature, which is also equal to wet bulb temperature and which is also equal to dew point temperature. So this is the point 4. So in this way we have located 3 points. Now we can read the enthalpies at these 3 points. So here it is the enthalpy scale, and these inclined lines are the constant enthalpy lines. So to find enthalpy at point 1, we can draw a line along constant enthalpy from point 1 like this. Similarly, from point 2, we can draw a line like this, and from point 4, we can draw a line like this. And we can read the enthalpy values. So here it is enthalpy at point 1, that is H1, it is 85.20 kilojoule per kg of dry air. Here it is enthalpy at point 2, it is 50 kilojoule per kg of dry air, and here at this point enthalpy it is 37 kilojoule per kg of dry air. Similarly, we can find out the specific humidity or humidity ratio for these points. So here on y-axis, these values are for moisture content in kg per kg of dry air, which is specific humidity, or it is also called as humidity ratio. So from these 3 points, we can draw a horizontal lines like this from point 1, then from point 2, and from point 4. And we can read the respective specific humidity value. So specific humidity we can indicate with small w. So for point 1, it is W1. It is above this 0.017. So here W1 it is 0.0172 kg per kg of dry air. For this point 2, W2 it is 0.010 kg per kg of dry air, and for this point 4 it is in between this 0.009 and 0.010. So it is W4. So W4 is equal to 0.0094 kg per kg of dry air. So from psychrometry chart we have found the enthalpies and specific humidity values at point 1, at point 2, and at point 4. Now we have to calculate total cooling load. So to calculate total cooling load, we have total cooling load is equal to mass flow rate of air into change in enthalpy across this cooling coil. So mass flow rate is m3 into change in enthalpy it is h3 minus h4. So this is the formula to calculate total cooling load. Now here enthalpy h4 is known to us, but enthalpy at point 3 is not known. Also m3 is not known. Mass flow rate of air is not known, but we know volume flow rate of the air in meter cube per minute. So we have to calculate H3. So to calculate enthalpy at point 3, here point 3 it is after mixing the fresh air and recirculated air. So to find H3 after mixing, we have fresh air 20% of total air and recirculated air it is 80% of total air by weight. So we can write the energy balance formula, that is 20% means 0.2 of enthalpy respective to fresh air, that is H1, plus 80% means 0.8 into enthalpy respective to recirculated air, which will be equal to H3, that is enthalpy after mixing. Here H1 and H2 we have got from the psychrometry chart. So by putting these values, we will get H3 is equal to 57.04 kilojoule per kg of dry air. Similar to this, we can find out the temperature at point 3. So TD3 is equal to 20% of fresh air. So temperature respective to fresh air, it is TD1 plus 80% of recirculated air. So 0.8 into temperature respective to the recirculated air, that is TD2. So from this we can calculate the temperature at 0.3, that is after mixing, which is equal to 28 degrees Celsius. Now to find the mass flow rate of air, we need specific volume or density at 0.3. So we will locate this 0.3 on psychrometry chart and we will read the value of specific volume from the psychrometry chart, and by using this volume flow rate and specific volume we will calculate mass flow rate of the air. So let us locate 0.3 on psychrometry chart. So 0.3, it is after mixing fresh air, that is outside air, and room air. So let us connect these 2 points. So 0.3, which is after mixing, will be on this line. So here at 0.3 enthalpy is 57.04. So on this enthalpy scale, here it is 55, then 56 and 57. So from this we can draw a line along constant enthalpy line like this, and intersection point of these two lines will be 0.3. Now in previous slide, by using this formula, we have calculated temperature at 0.3, that is TD3, 28 degrees Celsius. Now here we have located the 0.3 by using enthalpy H3. So we can read the value from here also. So if you draw vertical line from this, then here this temperature, it is TD3. So here it is 25, 26, 27 and 28. So TD3 is equal to 28 degrees Celsius, which is same. Now we have to find specific volume at this 0.3. So this inclined line, it is for constant specific volume line, and its value is 0.85 meter cube per kg of dry air. Then this line, it is for specific volume equal to 0.90 meter cube per kg of dry air, and we have to find out specific volume at 0.3. So we will draw a line parallel to this constant specific volume line from 0.3 like this, and we will read the value of specific volume for this line. Now here for this line it is 0.85 and for this line it is 0.90. So this line, it is not exactly at midpoint, so it is slightly on left side. So if this line would be at mid of these two lines, then it will be average of these two value, that is 0.875. But here it is slightly on left side, so we can say its value is 0.86 meter cube per kg of dry air. Now to calculate more accurate value of specific volume at 0.3, we can measure the distance between these two lines, that is specific volume is equal to 0.85 and 0.90, and also we can measure the distance between this 0.3 line and 0.85 line, and we can calculate more accurate value of specific volume at 0.3. So here the distance between this 0.85 and 0.9, it is 60 mm. Now depends upon scale of this graph, this value may be different. Here it is 60 mm. So for 60 mm distance, change in specific volume, it is 0.90 minus 0.85. So it is 0.05 meter cube per kg of dry air. So for 60 mm distance, change in specific volume, it is 0.90 minus 0.85, which is equal to 0.05 meter cube per kg of dry air. And here this length, the distance between 0.3 line and 0.85 line, it is around 22. So for 22 mm, how much will be the change in specific volume? So we can calculate this change by using 22 into 0.05 divided by 60. So 22 into 0.05 divided by 60 is equal to 0.0183. So for this 22 mm distance, change in specific volume is 0.0183. So the specific volume for the line passing through 0.3, it is 0.85 plus this change, that is 0.0183. So specific volume at 0.3, it is 0.85 plus 0.0183. 183, which is V3 is equal to 0.8683 meter cube per kg of dry air. So specific volume at point 3, it is 0.8683. So we have found the specific volume V3 from the psychrometric chart. Now here we have to calculate the value of M3, that is mass flow rate of air which is passing over the cooling coil. So mass flow rate M3 will be equal to volume of air divided by specific volume of air. So volume of air it is given 4500 meter cube per minute, and specific volume just now we got from the psychrometric chart. So this V3 it is in meter cube per minute, so we can convert into per second. So 4500 divided by 60, it is meter cube per second divided by specific volume 0.8683 in meter cube per kg of dry air. So we will get mass flow rate of air at point 3, it is 86.3756 kg of dry air per second. Now to calculate total cooling load, we have mass flow rate of air, then enthalpy H3 and enthalpy H4. So by putting these values, we will get total cooling load is equal to 1730.9685 kilowatt. So this is total cooling load on the cooling coil. Now we have to calculate room heat gain. So to calculate room heat gain, we have calculated total cooling load is equal to 1730.9685 kilowatt, and we have total cooling load is equal to room heat gain plus outside air heat, and here we have to calculate room heat gain. Total cooling load is known to us, so if we calculate outside air heat, then we can calculate room heat gain. So to calculate outside air heat, we have formula M1, that is mass flow rate of outside air, into change in enthalpy. So enthalpy of outside air minus enthalpy of room air, that is recirculated air. So here H1 and H2 known to us. So we have to calculate M1, that is mass flow rate of outside air. So the mass flow rate of outside air, which is fresh air, it is 20% of total air. So we have calculated mass flow rate of total air, that is at point 3, it is 86.3756 kg of dry air per second. So mass flow rate of fresh air it is 20% of this total air. So M1 is equal to 0.2 into 86.3756, that is 20% of this total air, into enthalpy H1 is equal to 85.20 and enthalpy H2 is equal to 50. So by putting these values, we will get outside air heat is equal to 806.0842 kilowatt. So this is outside air heat. So to calculate room heat gain, we can rewrite this formula as room heat gain is equal to total cooling load minus outside air heat. So by putting value of total cooling load and outside air heat, we can calculate room heat gain is equal to 1122.8842 kilowatt. So this is room heat gain. So in this problem, we have to calculate up to this only. Now suppose we have to calculate room sensible heat factor line, then we can connect this room condition with the apparatus dew point temperature. So here at point 4, that is condition of air after passing over the cooling coil, it is saturated air. So we can consider the temperature of cooling coil equal to temperature of saturated air. So here this point 4 is nothing but coil temperature, or it is also called as apparatus dew point temperature. So to draw room sensible heat factor line, we can connect apparatus dew point temperature with room condition like this. So this is room sensible heat factor line, and to locate grand sensible heat factor line, we can connect this mixing point with ADP like this. So this is grand sensible heat factor line. Now we can calculate value for room sensible heat factor and grand sensible heat factor. So to calculate value of grand sensible heat factor, we can draw a line parallel to this grand sensible heat factor line from this alignment circle. So this is alignment circle, and we can extend up to this sensible heat factor scale. So here we can read the grand sensible heat factor value. So this value it is 0.76. Now suppose we have to calculate value for room sensible heat factor. So we can draw a line parallel to this room sensible heat factor line from this alignment circle, and we can extend up to this sensible heat factor scale, and we can read the respective value. So room sensible heat factor it is 0.8. Now here this 0.4 it is the condition of air after passing over the cooling coil. So condition of air after passing over the cooling coil and apparatus dew point temperature it is same. So here effective room sensible heat factor line and room sensible heat factor line are coinciding, and temperature of air after passing over the cooling coil it is same as cooling coil temperature. So in this case bypass factor is 0. So when bypass factor is 0, room sensible heat factor line and effective room sensible heat factor line will be coinciding. Meaning is effective room sensible heat factor consider the effect of bypass factor, that is air which is bypassed from the cooling coil. So that amount of heat it is considered in the effective room sensible heat factor. So in this case, as bypass factor is 0, effective room sensible heat and room sensible heat are same. Thank you.